Welcome back to Lean Together 2026. We'll now have Floris van Doorn speak to us about the Carleson project.
Yeah, thank you for the introduction. So I will give a sort of retrospective of the Carlson project and talk about some of the lessons we've learned from the project. So I've already given a presentation about the Carlson project last year at Lean Together. And so the first 5 minutes or so will be repeating what I said last time, just to get to remind everyone what the Carlson project is, or for the people that didn't see my last talk. But after that, I'll talk mostly about new things. So before we start I should make one remark. You might have seen on the schedule that originally Christoph Thiele was going to give this talk, but unfortunately he was unable to do that due to health reasons. So I'm giving this talk for him instead and focus a bit more on the lean side instead of the harmonic analysis side. In this talk, I will give, of course, an introduction to the Carlson theorem, but I will focus on sort of the design decisions we made in the project, and I will focus especially on the decisions for the blueprint writing. So in my last talk, I spent some time on the formalization design decisions. I'm also happy to talk about that in the Q&A, but I will focus on the more blueprint design decisions and then talk a bit about the exciting next steps we have planned. But let's first talk about what is Carlson's theorem itself. Carlson's theorem talks about Fourier transforms and Fourier series. So here's a brief reminder for people that haven't seen this for a while or haven't seen this before. So we're talking about functions from in the basic form, say from the real numbers to the complex numbers. And let's say that's a 2 pi periodic function. Um, then we can define its Fourier coefficients as multiplying the function by this imaginary exponent of x, and then integrating it over like the periods of the function and averaging it. So these are the Fourier coefficients of the function, and then we can define the partial Fourier sum as like summing from there should be an n equals here n from minus n to n of like these partial Fourier sums as e times e to the I n x, and this is just an analog of sort of projecting the function into the sort of the first basis components of the space spanned by the smallest frequencies, and then the larger that n is, sort of the more well this approximates your original function. And indeed, if f is smooth, then these partial Fourier sums converge or uniformly to f as capital N goes to infinity. And then Carlson's theorem gives an answer to the question, what can we say about these partial Fourier sums under just very weak assumptions on f? And so this is a theorem from the 60s, and this says that if the function I started with is an LP function for p greater than 1, so this means that the if you take the norm of the function and take that to the power p, that is an integrable function on its periods. And then the theorem says, oh, pointwise, these partial Fourier sums converge to your original function for almost every x. So it's not true for every x. There might be a set of measure 0 where this doesn't hold, but for almost every x, this is true. And so this was proven by Carlson first for p equals 2, and then there's a technique using real interpolation to get this for all the other p's. And what is interesting about this theorem is sort of all the known proofs of this theorem are hard. So this theorem has been generalized over the decades since then, and has found new applications. And some parts of the proof have been simplified a bit, but there's still a core part of the proof that is still like a very hard argument. And also for p equals 1, this statement fails badly. So there are integrable functions where these partial Fourier sums just converge nowhere, or converge but to points other than f. Um, so that's all I want to say briefly about Carlson's theorem. So this Carlson project had as aim to not just formalize this theorem, but formalize like a modern generalization of this theorem. So this was proven by the harmonic analysis group here in Bonn, Lars Becker, Rajula Srivastana, and Christoph Thiele, and an external collaborator, Asghar Janeshyan. So they gave a proof of generalization of Carlson's theorem to so-called doubling metric measure spaces. So instead of the domain being the real numbers, it's now a metric space with a measure with some doubling property. And then at the end of 2023, we started discussing to formalize this, and we decided we needed like a detailed blueprint, which my co-authors in Bonn wrote, and that blew out the proof quite a bit, both by adding a lot more details and also adding an appendix to give the reduction from the general theorem to the classical Carlson theorem, which is 30 pages out of these 150. And then, as many of you have probably seen, in the summer of 2024, I publicly launched the formalization as a collaborative project where I asked many contributors to formalize small parts of this project using the blueprint as a guide, and this was finished slightly more than a year later in July 2025. So here is the dependency graph. I mean, this is the dependency graph after the project was finished. So it's all nice and green. So this is generated by Patrick Massot's Blueprint software, which also gives these nice HTML pages. And sort of here, I've also indicated sort of the different parts of the proof. So the general result from 2023 is the largest part outlined in blue. The main theorem is this red theorem here, and then the green outlines are are techniques and reductions from the main theorem to the classical theorem. The classical theorem is of course at the bottom. And yeah, so here's also here I've also show what the classical Carlson theorem is in lean. So this is hopefully somewhat readable. So we say if f is a function from the reals to the complexes, and we assume that f is continuous and periodic with a positive period c, then so this is the notation for almost all real numbers x, these partial Fourier sums tend to the neighborhoods of f of x as the n tends to infinity. So one thing that is different in the theorem we formalized and the theorem I showed a couple slides ago is that here I assume that f is continuous. This was what we proved in the blueprint because it simplifies the argument of the reduction a little bit. But I have a student that is now working on properly changing the hypothesis that f is continuous to f is LP for p greater than 1. So that is still ongoing. So there's still some work happening in the Carleson project, some additions since the completion. And here I'll briefly show the main theorem. So this is the statement of the main theorem, which we've defined in a file that imports very little from the Carleson project, and then at the bottom in a completely different file is the proof of that main theorem. So this main theorem is much more complicated, and I don't expect you to read read the statement right now, but just to give you an impression that it's still stateable in a couple lines. And yeah, so we have a file with just def, which we call def.lean, which just is there to define the statement of the metric space Carleson theorem. So it's under 300 lines and even less if you exclude the blank lines and comments. And it only imports files from Mavlib or from the subfolder to Mavlib. So like every project, we have a to Mavlib folder that has results that should be upstreamed to Mavlib. Um, so now the project is done. That is underway. It's going a little bit slowly because I think some of the excitement has been lost since the project has been finished, and I've been busy with teaching. But I do want to push over the next couple of months to work myself on upstreaming and to ask others to help with upstreaming. And so for illustration, some of in the main statement, we've bundled some classes together, but I wanted to give you an impression, sort of what are the assumptions on the metric space X in the main theorem, and that's all these type classes. So we assume that X is a metric space with some topological properties. It has a sigma algebra and a measure on it, and then has some properties on the measure, including the last one, which is a property saying that the measure has a doubling property. So that says that a ball with radius like 2r is at most a times. So the volume of a ball with radius 2r is at most a times the volume of a ball with radius r around the same point. So that's why sort of the main result is for doubling metric measure spaces because yeah, that's all captured in these assumptions. So let me give some statistics on the project. So this here I've included some numbers about the project. So the Carleson project has 45,000 lines, of which 38,000 where with like 7,000 lines which are blank or comments. And then the to Mavlib subfolder has like about a third of that. So a significant part of this project is like consists of material that we want to upstream to Mavlib, and then sort of the main part of the proof is just done for this particular proof, and not we don't really intend to upstream that part. Yeah, so there's more than 500 PRs to Carleson, and actually some contributors like me have not always made their contributions with PRs, so there's probably a bit more commits. And in total, there are 31 contributors. Um, and yeah, there's like 2000 lemmas, 300 definitions, 30 new structures and classes. And one thing that I find interesting, there's no new inductive types defined in this project. So I think some people have said that, well, in if you're doing sort of pure math outside of logic and or discrete math, you don't really use this inductive types. And in analysis here, that seems also to be the case. Yeah, so we still need to do a lot of upstreaming work, but we've also done already quite a lot of work with Mavlib PRs for the Carleson project. So there's more than 100 already that were opened, where 90 or so are already closed. And this includes new material, but also refactors. So Michael Rafgang did a big refactor generalizing a whole bunch of the measure theory library to a new class called eNorm. And that refactor already touched 4,000 lines in Mavlib itself. Um, so now I want to talk a bit about sort of the design decisions we made for the blueprint and how well they played out. So I was not I did not directly take part into writing the blueprint, but I was of course involved in discussions about like what's already in Mavlib, what should be in the blueprint, how should we structure the proof? Can we sort of anticipate some pain points? Um, and one thing that I want to start with is sort of the consequences these some of these design decisions had for the blueprint, and that is that there were so during the formalization we found many smaller errors in the blueprint, but no significant mistakes. So there was nothing problematic in the blueprint that couldn't be fixed like easily. And some mistakes were like really minor, like small typos that could be easily fixed and spotted by the formalizer. And sometimes there was something like not quite right with the argument, or maybe another lemma needed a little bit of fixing. And there, Lars Becker from the PhD student in Bonn really helped with I mean really knowing almost the full proof of the blueprint by heart, and was able to like easily say what needed to be fixed for these when we spot on an error like this. So one thing that's interesting is that almost none of the mistakes we found were not part of the original proof, and maybe in a few cases that is because the original paper didn't have much details, but actually also in writing the blueprint, some decisions were made that maybe introduced more mistakes than really necessary. Um, and so I want to talk about that. But of course, I think it's also I think also an aspect is just well, if you write a whole lot more details and a whole lot more detailed proof, I mean, in the mistakes in the form of just typos or small, uh, yeah, mistakes in a single proof, they can of course slip in as well. But so one of the design philosophies for the blueprint that Christoph Thiele advocated for, and which also had like good advantages, is that in sort of the main part of the proof, we wanted to work with finite objects as much as possible. So examples of this are that in sort of the main part of the proof, we work with functions that are bounded and have finite support. So there's only like a finite set, like a set with a finite measure, and everywhere outside that set, all the functions we're considering are just zero, so we don't have to consider them. And also, I will explain this terminology on the next slide. We only work with finitely many cubes and tiles. Um, and yeah, so this was we made this decision to sort of simplify sort of the hardest parts of the arguments a bit because we only work with finitely many objects. And I should say that sort of the main result is not affected by this. So in our current approach, we first do everything with these like bounded functions with finite support, and then at the end we do a limiting argument, and with some limiting arguments, you still get sort of the full Carlson's theorem, generalized Carlson theorem that we want. So this is just a restriction in the proof, not in the statements that we proved and formalized. So what do I mean with these cubes and tiles? Here we have this metric space X, and we sort of subdivide this metric space into small pieces that we call cubes. So here on the left, we have this metric space, which we divide into cubes. And actually, every cube, there's a whole hierarchy of cubes. So at every level, we divide the space up into cubes. And in the sort of one level finer, one level higher, we have the cubes that are further subdivided into smaller cubes, and then a level higher, even smaller cubes. I should say here that these are not like normal Euclidean cubes, because we are working in a metric space, so we cannot define like just normally using Euclidean coordinates, anything. But this is just some axiomatized collection of sets that we, at the start of the proof, construct. That there exists such a subdivision of the space into cubes. Um, and we axiomatize some properties that we want. So the cubes should have sort of like a radius and diameter that are between two values, and the boundary of the cubes cannot be too complicated. Um, and we actually, so this is the subdivision of the space into cubes. We have a similar subdivision of the frequency domain. So the functions we consider, like they can be oscillating, and we also look sort of in frequency space of these functions. And there we do a similar subdivision of the frequency space into something we call tiles, but they behave very similar to the cubes. And there's actually a difference in the proof. In the paper, we consider the cubes indexed by the integers, and in the blueprint, there are finitely many levels. And so this simplified some arguments because we didn't have to consider sort of an infinite sequence of cubes. But it also required some extra arguments considering sort of the smallest level of cubes or the largest level of cubes. And those were sort of written specifically for the blueprints. And some errors slipped in there from adding this different proof in the blueprint. Here's a second thing that I want to mention. So we have we define the Hardy-Littlewood maximal function. So if you have a function from like a metric space X to the complex numbers, we can define the Hardy-Littlewood maximal function of that function as take a ball around the point X. Oh, so this should say MF applied to X. So take a ball around the point X with radius R, and take the average of your function, of the norm of your function over that ball, and then take the supremum of all radii R. So that's the standard definition of the Hardy-Littlewood maximal function. And in our proof, we used sort of a non-standard definition of this function, where we only consider either finite collection or countable collections of balls instead of all of the balls. So this has as advantage that some properties are a bit easier to prove. For example, the fact that the Hardy-Littlewood maximal function is always measurable. But we also had to keep track of the specific family of balls. So this was always possible in our proof, but it was also a source of mistakes. There were some proofs that were sort of mistakenly written in the blueprint because of this design decision. And so I think this was sort of something we shouldn't have done in retrospect. We should have just defined the standard Hardy-Littlewood maximal function and just proven the desired properties for that. So that is still something that we need to do before we upstream that part to Mathlib. But of course, this is definitely something we need to get into Mathlib. Yeah, so these are some lessons I think we've learned. So I think it's good to stay close to the literature. So don't try to do sort of like ad hoc changes to the proof to um, to try to make certain arguments easier, at least if the general case also works, especially if the general case is something you already formalized to get into Mathlib anyway. And yeah, so the point of all of this was to try to simplify the proofs so that the sort of formalization was simpler, but that actually introduced some mistakes in the blueprints. Okay, something that I think was a good design decision is that we worked with explicit constants. So in analysis, you often make like estimates of the form, oh, like f of x is bounded by a constant times g of x. and the constant can only depend on like certain parameters, not everything. And in both the blueprint and the formalization, we just worked with explicit constants, where we define the C as a separate definition, just depend as a function depending on the parameters that it can depend on, and then you plug in those explicit parameters. So in the blueprint, we also wrote it that way, and of course there were some calculational errors here and there, but those are all like easy to fix and didn't really cause any problems during the formalization. And one advantage this has is that at the end of the project, Sebastian came around and said, "Oh, can we optimize some of these constants?" And so without much effort. So one of the main constants that is used in the proof is this d, which is 2 to the 108 squared, and that can be like equally reduced to 2 to the 7a squared, but it cannot be reduced much further. Or at least it cannot be reduced much further with this exact proof. If you actually wanted to care about, if you actually care about these constants and want to minimize them, then you have to sort of parameterize a whole lot of things differently. Like this little a is parameterizing like 6 or 7 different things in the proof. And if they all had their separate parameters, you can optimize the constants further. But also, like in harmonic analysis, people generally don't really care about those constants. So that's probably not the most interesting thing. So in the last few minutes, I want to say a little bit more about the next steps that Christoph Thiele and I are planning. So as most of you probably have heard, we were awarded an ERC Synergy grant. So for the next 6 years, we're going to continue doing both research of like new harmonic analysis and formalize the resulting proofs, mainly to show like, hey, we can actually formalize like modern results in harmonic analysis, and to make that like an impetus to formalize more results like in modern research mathematics, which in certain areas are completely unfeasible, but in harmonic analysis that seems to be quite feasible. And so we'll focus on 3 things: ergodic averages, estimates of multilinear singular integrals, and nonlinear Fourier analysis. So I'll talk a bit about the ergodic averages, because that's sort of the next project that we're planning and which we've already started to work on. So this is a question in ergodic theory, and the the proofs of problems related to this often use harmonic analysis. So that's why this fits in this project. And so in ergodic theory, you consider like a metric, sorry, a measure space and transformations on these space that are measure preserving. So here we have a family of n measure preserving transformations that each pairwise commute. And you also have some functions that measure some property like position or velocity or something from your space. And you assume that these are like LP functions for some P. I don't want to be very specific, but I want to assume. And then the question is, can we say anything about this quantity? So this is sort of apply your transformation J many times and then measure what the result is, and take the average of the first like K measurements. And what can we say about this as K goes to infinity? So for n equals 1, sorry, and this 1 over n should be a 1 over k. That's a typo. For n equals 1, so if you have just one transformation, sort of this is answered by standard results in ergodic theory, like Birkhoff's theorem and the pointwise or the mean ergodic theorems. But if you have commuting transformations, the story is a lot more complicated. So, for example, Terence Tao proved in 2007 that these functions n, k converge with respect to the L2 norm. And then a research project of Christoph Thiele and co-authors was to give a more quantitative version of this convergence. So there's something you can define called the variation of such a sequence. And in 2016, he posted with co-authors result that for n equals 2, if you have two commuting transformations, that these MKs have bounded variations. And a more recent paper showed the same result for for n equals 3. And one conjecture that we are currently working on is showing that this actually has bounded variation for all n, and we also want to formalize this in lean. And then a much harder conjecture is that actually there's a notion of pointwise convergence, and even for n equals 2, that is very hard. So with that, the takeaway is I think that like modern and recent results from harmonic analysis are already ready to be formalized in Lean. And so thank you very much for listening.